So hi, and warmly welcome to this webinar in the FibRe and Treesearch online seminar series. This is, I think, we have got it to the 16th in the series. So that's something. If you haven't checked out the others, you can find them on Treesearch YouTube or on our webpage. But today we are very happy to have Professor Antje Potthast from BOKU with us, and we will give you a proper introduction in just 1 minute. I would just say that you in the audience, you're very welcome to ask questions. You are on Zoom, please use the chat, the Q&A function, or raise a hand. We will have a Q&A session afterwards. You on YouTube, you can type the question in the chat and we will help to get you answered. But for the presentation of today's speaker, I hand over the word to Professor Lars Wåhlberg.
Yes, thank you so much, Josephine, and warmly welcome to everyone to today's seminar. We are so happy to have Professor Antje Potthast from BOKU in Vienna with us. I learned yesterday that BOKU stands for Universität für Bodenkultur, and you have been a professor there, if I read up correct on the internet, since 2018. But today's topic is on characterization of celluloses when it comes to their molecular mass and their molecular properties. And you all collect libraries of our own on our computers or in the bookshelves. And I read a lot of papers by Thomas Röder, an Austrian, and then I went back to look at the papers, and then one of those papers is entitled "The NMMO System Revisited." And then I read the author list there, and actually Antje was one of the authors of that publication. So this is not something that has popped up in Antje's interest lately. This is a long time experience that we are happy that you can share with us. And by that, I give the word to you, Antje.
Yes, thanks a lot. So actually, Thomas Röder, we studied together in Dresden 30 years ago. So Tom is a long time friend of ours. Thanks a lot for the invitation. So today's topic, I will try first to share my screen. So hope this works. Swap this. So do you see the full mode?
Yes. Perfect.
So today's topic is segmals of oxidized celluloses, something, let's say, cellulose oxidation we're really working on since 25 years now. So, and since you are also quite interested in periodate oxidation, I made this a large portion of the talk. And what you can expect in the next roughly 30 minutes is that I will start covering why segmals. So what's the advantage here? Why would it make sense to know the radius of gyration in that specific setting or topic? I will very briefly talk about carbonyl group determination because this comes naturally with oxidation, and also here segmals can give us some clue. And the major portion will be on the stability and dissolution issues. And this is something we are really facing in this topic. And for some, there is no solution, but for some issues, there's a little bit of workaround, and this I want to share with you today. So oxidative modification. We can basically divide them into intentional and non-intentional oxidations. The most straightforward oxidation is natural aging. So their oxidation just happens on a slow speed. We cannot stop it. We can just slow it down. And then we have a number of oxidations occurring also in an unwanted way. And this is usually during bleaching, where we try to get rid of something else, either chromophores or lignin. And along with that, usually we have some oxidative damage of our cellulose. And then we have those which happen intentional. One example is here all the way to the right, this molar mass adjustment as we have in the rayon process. It's also called aging, but it's a different aging where we use an aging to adjust the molar mass of a cellulose. And then, of course, we have the real chemical modification. And here we have as the major examples, temper oxidation and periodate oxidation. And this is what I will mainly cover. I guess you're all familiar with the periodate oxidation. It's a very specific process. The reaction is very old, and it opens up the C-C bond between the C2 and C3 in our cellulose backbone and introduces two aldehyde groups there. There is almost no other process and no other, I wouldn't say no other, but very few chemicals can basically do that as good as periodate can do it. And those two aldehyde groups we introduce in the anhydroglucose unit by that process, they do what aldehydes do. They form hydrates. That makes them, at least with low degrees of oxidation, almost invisible in the FTIR spec. But they also engage with neighboring OH groups, and they form hemialdehydes, hemiacetals, and cross-links. And that cross-linking is the problem why we run into insoluble material. It's for every polymer, if we start cross-linking at a certain point, it becomes insoluble. There's nothing specific to cellulose. But here, the process is in a way quite dynamic. It's not very well controlled, and that causes a lot of troubles when we want to analyze that materials. So this is something we always have to keep in mind. Temper oxidation is again a very rather selective process. We oxidize the C6 first to this aldehyde group and later on also to the corresponding carboxyl group function. Some of the aldehydes usually survive if we not further oxidize them to 100% to the carboxyl group acid, or to the carboxyl. So also here we're running into issues of insolubility at high degrees of oxidation, and just the final product, which is called the polyglucuronic acid, again becomes water soluble and can be then measured in an aqueous SEC version. Now let's start with a very common pitfall for SEC in oxidized celluloses, and this is again, already an example from periodate oxidation. So if you go to the early literature of periodate and SEC, and here we're talking about moderate and low degrees of oxidation, so the starting material, which is the cotton linters here, has 26 micromoles per gram, and we oxidize until roughly 167 micromoles per gram. And what we see is that our SEC moves to the right direction, so our retention time becomes smaller, and as you all know, SEC separates according to the hydrodynamic radius. And if the hydrodynamic radius becomes smaller, we think the molecule is smaller. And if you go to the literature, and unfortunately you also see it until very recently, the conclusion is, okay, this periodate oxidation degrades the cellulose. I'm not saying periodate oxidation does not degrade cellulose, but it's not true for these degrees of oxidation. Because if we now add a mass detection system, so light scattering, which gives us absolute numbers for molar masses, we see that those very different retention times fall into basically one curve, which means they still have more or less all the same molar mass. So there is no degradation. And if you look at the 83 micromoles per gram curve, it even looks a little bit larger. And this is where the cross-linking starts to occur. So moderate periodate oxidation initially does not lead to a degradation, and you have to be very careful with oxidations if you conclude from a conventional calibration with standards, or just looking at the retention times, that you draw the right conclusions. Now, why is that? As I said, the SEC works according to the hydrodynamic volume of the molecule in solution, and usually cellulose has a rather large hydrodynamic volume in dimagnesium chloride. This is our solvent of choice. So we have a certain radius. Let's see if you can see it here, my pen. So that would be our non-oxidized cellulose. Now we oxidize the cellulose in a periodate mechanism, and then that cellulose starts to cross-link. So the cellulose backbone, so this is still the same, it just adds one cross-link. So our molar mass is basically the same, but our radius changes. The molecule now becomes a lot more compact. So we have here a really smaller radius, and of course this molecule elutes later in SEC, which suggests that we have a smaller molecule, which is true, but the molar mass is still the same. So solution structure does matter, and we can address that by light scattering if our molecule is large enough. If the molecule is large enough, we can not only measure the molar mass distribution, we can also measure the radius, and in that case, it's the radius of gyration. Why we can do that? If the molecule is very large, then our scattering intensity gets into an angular dependency. So at different angle of scattering, we measure a different intensity. And for an anisotropic scatterer, and this is the case if we have about a molecule which is larger than 1/20th of the wavelengths we are using for our light scattering, we basically can see that, and based on that angular dependency, we can calculate this light scattering radius or radius of gyration. For ligand molecules, for instance, we mainly have isotropic scatterers, so the molecule is too small, and here we don't see that angular dependency. For cellulose, it's okay, we do see it, and we can use it. So if we look what we have here now, normal cellulose is not cross-linked, and then if we introduce our aldehyde groups which have the ability to cross-link, we can have two types. One is the intra-chain connection, so the intra-chain cross-linking, that would be this case here. This shows us the more compact molecule, but we can also have an interchain cross-linking, and this leads to larger molecules. And this we can see when we look at the conformation plot, which is a double logarithmic plot of the molar mass we measure by light scattering, and this radius of gyration in our solution. And this you see here on the right side. This time we see that here for a tempo example. And the black curve, so this one here, this is our starting material. This is our non-cross-linked cellulose, which has at a certain molar mass, we just pick one here, we have a certain radius in solution. So quite large, as I said, but that's the typical case for cellulose. Now we start to oxidize, and we can still dissolve those samples, so oxidation degree is not extremely high. The time we have here is just the time of oxidation for tempo. And then we see at the same molar mass, so at the same molar mass, our radius becomes smaller. And if we do that even more, so we oxidize longer, it becomes even more small. And then after that, we run into insoluble fractions, so we cannot dissolve this anymore. So we have still the same molar mass, like here, but we cross-link and the molecule becomes more compact. And we can basically say from the conformation plot, or we can judge the degree of cross-linking. And if you have a strictly linear molecule, you can even calculate the number of cross-links. And of course, the same thing also happens or works for pyridate oxidized celluloses. We see the same thing here. We have here the conformation plot, and the more we oxidize, the more flat becomes this conformation plot, and we can indicate from there that we have cross-linking. This is usually not a very reproducible process. So if we measure the cellulose, the slope of the conformation plot for a typical cellulose is somewhere between 0.55 for classical paper pulps and dissolving pulps. If we have annual plant fibers, it goes a little bit up, so 0.6 something. We usually measure for cotton and for other annual plant fibers. And then if we have cross-linking, we come down and becomes more flat. So there is a certain dynamics because our hemiacetals, they open and close. We cannot prevent completely during our dissolution that we really open them all up. So some remain, and we see that in the conformation plot. And there is a direct relationship to our degree of oxidation, which is the number of carbonyl groups or aldehyde groups we have here. On the left side, we see the aldehydes. So low degree of oxidation. Here, this is in the range of a natural cellulose. There is basically not much difference, but when we then start to oxidize, our slope of the conformation plots drops down, and until we run into non-soluble fractions. And we can also now go to the other side because we are opening up the C2, C3, and if we now reduce that same dialdehyde cellulose, for instance, with borohydride, I will talk about this in a little bit, we see the opposite effect. The slope of the conformation plot goes up because now we prevent cross-linking because we remove our aldehyde groups. And now the cellulose molecule becomes a lot more flexible because we have opened up the C2, C3, CC connection. So, and we see that our slope of the conformation plot raises to 0.8 something. All right. Now, very quickly into this carbonyl group determination. I don't want to go into details here for the method. It's long known. We call it the CCOA method. What we do is we attach a fluorescence label to a carbonyl that can be a keto group or an aldehyde group. We cannot distinguish between keto and aldehyde groups. But by doing that prior to dissolution and SEC measurements, we basically can trace the carbonyl groups along the molar mass distribution. And we can also, of course, measure a total amount. And we see that here on the left side. The major introduction happens here in the smaller molar mass areas, but also we introduce some in the high molar mass area. If we increase even our degree of oxidation, we see cross-linking. So we have an increase or an apparent increase in molar mass and also carbonyl groups here. That is basically carbonyl groups along the molar mass distribution. Sometimes you just want to know a bulk number, some parameter, and this you can do basically by a method we have established a while ago. This is chemometry connected to NIR or FDIR. So we measured for quite a number of samples the carbonyl groups with different methods, but mainly oxide methods and the classical UV. method which just uses the depletion of periodate. And if you correlate that, you have the chance to predict the total amount of introduced aldehyde groups in the periodate oxidation by a simple NIR or FTIR measurement. We made this raw data available, so you can basically take them out of the literature and use them under certain circumstances in your own measurements, without that you have to measure the 75 samples and have to do all the analysis. So this is available in the literature, and you're free to use that and make your life a little bit more easy when you just want to measure some parameter, so the total number of aldehyde groups you have introduced by, for instance, periodate oxidation. Now, stability and dissolution issues. We rely on a certain stability when we do an analysis or when we want to measure something. And this, of course, also applies to SEC. And of course, we have to make sure we don't degrade the polymer backbone during any thing in terms of measurement or changing pH. And beta elimination is something which is, I would say, unique to cellulose. Beta elimination just means if we have a keto group, either at C2, C3, or C6, we split the adjacent beta to Dutch keto group glycosidic bond. No matter where that is in our anhydroglucose unit, we split a bond either left or right to our anhydroglucose unit. And this happens not only for periodate, this happens for every keto group. So that means oxidized celluloses are quite sensible against alkalinity. And this is also true for periodate oxidized celluloses. And we always have to be aware that this can happen. And the usual workaround here is that we say, okay, let's do a sodium borohydride reduction. And this is also, for instance, true if we measure viscosity. The solvents for viscosity measurements in the pulp and paper industry are usually highly alkaline. And if we would go in there with an oxidized cellulose, we would degrade the cellulose during dissolution, and we would not be able to get the original molar mass or viscosity of that sample. So the classical workaround is, okay, let's do a sodium borohydride reduction, and then we are arriving at more or less the original number. Yes, that works for slightly oxidized celluloses, usually in a good way. It's a little bit more complicated for periodate. The problem is that in sodium borohydride reduction, we do that under alkaline conditions. Otherwise, borohydride would not be stable. So pH is around, let's say, 10. So we have an alkaline environment, and we have a reductive environment. And now beta elimination due to the alkalinity and reduction proceed at the same time. And the question is just, who's winning? So what is faster? If you look here at our softwood kraft pulp we used for the studies, we have MW of about 600,000 grams per mole. Then this is oxidized towards different degrees. And then we basically see that even if we do this reduction, our molar mass really drops down. It levels off. It's this classical leveling off dP of oxidation. We think the reason is that the oxidation is a heterogeneous process, cannot enter inside the crystals. So there is this level of material still there. But otherwise, we have basically a drop in the sodium borohydride reductions. This is the green part. And the red curves here those are just alkalinity. This is just the beta elimination. And the curve is slightly lower, but roughly we arrive at pretty much degraded celluloses. That means our periodate oxidized material has a limited stability only under alkaline conditions. We can also look at the molar mass distribution here and the dependency on the pH. We see that here, this is a little bit more acidic, more alkaline, and we have this shift over here towards lower molar mass distributions. So not stable. What can we do? We can first look into the borohydride reduction. It's a very fast process. We see that here. So we come from a pretty oxidized pulp, degree of oxidation around 40. Within the first 6 minutes, we drop down and we really reduce to about 100. So this is just a zoom out of this area down here. And then we can really reduce it, and we can measure the remaining aldehyde groups, and we measure that with the CVOA labeling. But reduction in molar mass also happens basically simultaneously here. The only thing what we can try to do is we can increase the equivalence of borohydrate in order to slightly slow down that process. So we offer a lot. That's not an economically feasible way of doing a reduction. But we see here that if we offer 50 equivalents, we have a MW of 173, while with just 5 equivalents, we have roughly half of that. So if we add a lot, that can basically preserve a little bit our molar mass stability. Okay, so which means that reduction is not the way to go in order to figure out what is the molar mass of our dialdehyde cellulose if we basically exceed the soluble portion in dimagnesium chloride. So this dialdehyde cellulose above 2% and below 80%, where DAC then becomes water soluble, this is still some sort of a black box. And this is what I will cover in the last part here. So again, slightly oxidized celluloses, and this also applies to cellulose 2, like a rayon, is accessible with SECMALs in dimagnesium chloride. The cellulose 2 may require that you add a little bit of DMSO in the activation step to increase the swelling, but we can measure it. The highly oxidized version, so above 80%, which is water soluble, we have 2 options of measuring. We can use an aqueous sec, what you basically see here on the right side. This is a combination. So this is the starting material. This is a cotton linters. This was measured in dimagnesium chloride, so we cannot measure that in water, but SECMALs, so we can compare basically the absolute molar mass distribution. These measurements are done in water, in an aqueous sec, and we see basically the shift in molar mass. We have to say that those aqueous solutions of DAC are not super stable. So I would say if you measure those secs in 3 different weeks, there's a lot of aging involved here. You probably get a lot of dynamics. You have a lot of opening and closing of crosslinks here. So it's not a very reproducible material. But it's water soluble, and you get a rough idea on the molar mass distribution. And what you don't see here is that in that aqueous solutions, besides what we see here in terms of really soluble material, there's also aggregates in there. And those we can address with a method called asymmetric field flow fractionation. It's again coupled to moles. Here we have the portion we see also over here. But what we have here is a low concentration, but still large aggregates which are present in that solution. So as I said, there's lots of dynamics in here. All right. Now one workaround to address this black box in the middle. So we do a periodate oxidation, and we do that towards a degree of 20, 30, 40%. And we still want to measure that. And one way of going around the problem we have is basically we have to prevent that the cellulose, the oxidized cellulose, can do the cross-linking. And this basically we can do by blocking the aldehyde groups by a simple oxime. So we cannot reform basically that cross-linking, and that should basically prevent our solubility issues. So with that, we can address the molar mass of this material because it cannot do this anymore, and we measure it as the corresponding oxime, and at the end we should be able to see what we are not able to see, the real, or let's say the molar mass distribution of our actual oxidized dialdehyde cellulose. And here the studies were that we checked a lot. Is it stable? Is it stable during oxidation? Are there any other degradation reactions? And the oxidation GPC approach works nicely for, I would say, this intermediate degrees of oxidation. We have here a 7%. There is no way we can measure that in dimagnesium chloride directly, but we see basically that we get stable data for the oxidation. We also see there is a degradation. So now we really have a degradation. And this is now not induced by the GPC. This is in a way real. Something like this can now basically be measured. And we can also now follow our oxidation. So time here is time of oxidation. And we can follow the molar mass degradation basically during its oxidation. What we see here on the right side is 0.5 equivalents of periodate, and on the left side here we have different concentrations, and we see basically how our molar mass basically develops. The oxidation as such is not a way to stabilize against beta elimination. So the molecule still becomes or is labile under alkaline conditions. We see that here. This is a comparison between oxime and non-oxime periodate oxidized celluloses. But the oxime per se is more or less stable material to measure a second dimagnesium chloride. So that works quite nicely. It's a little bit of workaround for those invisible range where we are interested in still in the molar mass distribution. All right, so this is basically it. So I hope I could show you a little bit that the measuring of oxidized cellulose is not super straightforward, but I think we can have some workaround protocols here, and we have some points where we have to be a little bit careful. But I think we get a very good idea on how we can basically address smaller masses of those oxidized celluloses. But I think there's still a lot research to do for the younger generation. So there is still something left to research, and I'm happy to answering any questions if I can. So thanks a lot for your kind attention. Maybe just a very quick acknowledgement. I would like to thank our industry partner, which is here in that project, UPM in Finland. Biorefinery Center Tulln, the County of Lower Austria Doctoral School, who supports Jonas, the PhD student, and our collaboration partners at Alto and those in the lab helping us. Thanks a lot for your attention.
Thank you so much, Antje. That was a very, very insightful and clear presentation. So really appreciate it. Thank you so much. So I wonder, Annette, would you like to run the questions, or how should we do it?
We help each other, I think.
Yeah.
Do you want to start, or?
Yes, I try to use my labeling here just to make an applaud, but I was obviously raising a hand, so I can raise a hand. No, there was a lot of to start. I had two questions. That was in your slide 9 and 10. Was that what was the solvent there? Was that lithium chloride dimethyl acetamide?
Yeah. So our solvent is always dimethyl lithium chloride.
Okay, and then you mentioned in your slide number 12, I think. Okay. You mentioned that.
Can you see it?
Yes, there. No, that was maybe it was you changed your you changed when you're changing from dialdehyde cellulose to dialcohol cellulose. You also change the interaction with the solvent. Have you looked a lot? Have you looked? And I mean, it probably would turn up as a second change in the second virial coefficient or something. Have you looked a lot on that, or?
We have not done any static light scattering on that. We can also assume that dN by dC will change.
Yes.
We did not really. I mean, it's very hard to measure for cellulose. And it would mean basically that you're able to address the concentration very accurately, you dissolving, which is already difficult for cellulose. It's also very difficult for dialdehyde cellulose, and even more so for dialcohol cellulose. The reason is because you have to go through a solvent exchange where you cannot be sure that you collect every little molecule of cellulose in your filters. But the change is so large in a change in the slope of the conformation plot that we can assume that is real effect.
Okay.
One thing you always have to keep in mind is your slope in the conformation plot also changes when you have a very bad state of dissolution. So if you would use a solvent which is or let's say you do a very bad solvent exchange, you get something in solution and you get some weird effects also. Then the slope of the conformation plot will change. So if there is no reason for cross-linking because you just have a cellulose, nothing else, no oxidized cellulose, then you have to be careful drawing conclusions just from the slope of the conformation plot. You have to make sure your solvent is powerful enough to dissolve your material.
Now we have been when we have been looking at this, and the Per can probably chip in more on that, but we have seen that when we are changing from dialdehyde to a dialcohol cellulose and from non-oxidized cellulose, we see that on a macroscopic level, the fibers or the fibrils will change the macroscopic structure.
Yes.
And we don't know exactly what, if that's a solvent water cellulose interaction or what we are seeing. We haven't been able to pinpoint that. So that was one of the backgrounds to the questions.
Okay.
Maybe you're seeing the same things. I mean, that's so if you have a fiber dispersion that you oxidize, you will see a macroscopic change in the structure when you are oxidizing it. And I don't think it's a more solvent interaction parameter that we're looking at. Yeah, sorry.
This is in solution. And so what we see here is really what is in solution. We have separated molecules there. This macroscopic effect, I think this is really something where we have morphology changes on the fiber surface. So we lose a little bit the fibrous structure, I would say, right?
Okay. Interesting. Well, those were the most obvious questions I had, and that's maybe we should leave it to someone else to ask questions as well.
Yeah, I can continue when we are waiting for questions in the chat and Q&A. So here I see in one of the slides you had the error bars. They were stated that you had them to, yeah, here it is in the left hand that the error bars is stated at 5%. So I was thinking about when you take this slope, have you seen, is the slope constant over the whole peak, or do you get different slopes, if I say so? So depending on that, if you have more oxidized, then you have maybe smaller, and then they have one slope, and then they have come later, or how does it work?
It's constant across the majority of the peak. At the edges, so you always have a lot of deviation, and it depends a little bit on your scattering quality you have. So, for instance, we are running celluloses only with 488 nanometers, so with a blue laser, because the scattering is better in that range. The N by DC is larger and so on. But you have to cut away the high molar mass because their scattering is nice, but the concentration is low. So RI is not a very good detector. On the low molar mass side, it's the other way around. The scattering is bad, even though if your concentration is still acceptable. So what you see here is basically extrapolated, but over the linear range of the molecule. And if it's not linear, something is wrong, I would say. So if the conformation plot is like S-shape or something, then you have usually a very bad state of dissolution. And you already see that from the calibration in the light scattering. So if your calibration should be linear because you're using linear columns, and we are using linear columns for that reason. And if you have an S-shape calibration line, then your state of dissolution is in a way that it's not acceptable. You have to do something, or you cannot use data.
Yeah, Lars, I think we have some questions in the chat. So,
yes.
Yeah, we also have, we can allow you to talk back if you, and you can say your question.
Okay, can you hear me?
Yes.
Yes.
Thank you, Antje, for a very nice, very nice and pedagogical presentation. You may correct me if I'm wrong on this statement, but at least literature claims that dialdehyde cellulose is soluble in hot water. Would it be possible to run SiC at a higher temperature and simply avoid further derivatization by having it dissolved, or do you disagree and think it's so with the increased solubility that is claimed in literature?
Principle, it's possible to run SiC under high temperature. There's even for certain polymers a high temperature option. I think what you refer to is just to use maybe 80 degrees in the column oven. Exactly. But then you have to consider that your autosampler is not at 80 degrees. So you basically have you have a sample solution. You can heat that up, but it will cool down whilst in the autosampler. And then you inject, something cold on a very or rather hot column. So you have a temperature difference of, let's say, 50 degrees at least. And I think in a dynamic system like this, you really run into something not very well reproducible. So you can do that, but I would not recommend it. I think it will not help you a lot. Okay. The problem is if you heat it up, or if you heat your sample, and if you reach a state when you cool it down, it stays in solution. That would maybe help. But heating up something in dimagnesium chloride, which is our solvent, is not a good idea because as an intermediate, you form something. There's a publication from us on that long time ago. you form a species which cleaves your glycosidic bonds. So heating N-dimethylglycerin chloride is nothing we do. So we run everything really on room temperature, maximum 35 degrees. And this is just the temperature setting of the RI detector. And the aqueous sec, same thing here. There, once the DAC is in water solution, and this really depends on the degree of oxidation of your DAC, then it stays there, but this is usually accompanied by degradation reactions. So I don't think if you heat it up, you get what you're looking for, because you don't do the derivatization, but you do the degradation during the heating. And but this is just speculation now from my side. We would need to try it, but in general, the water solubility only comes at a very high degree of oxidation. So for those intermediate versions, it's harder.
Okay, thank you. And unless there are other questions, if I may ask one more, or ask you to speculate, the question that Lars sort of touched upon but didn't really formulate. You might be aware that if you have fibers, it can be a paper. There's a report where the authors place one of their business cards in sodium periodate solution, and it shrinks to 1/4 of the area. So basically, any cellulosic object, if it's a fiber, a CNF, or I guess also a regenerated, dissolved, more amorphous cellulose object, it all shrinks in sodium periodate. And that has bugged us for years. Do you dare to speculate why this happens?
Well, I mean, maybe that's the same what we see on the molecular level, cross-linking.
Yeah, that's one of the hypotheses we addressed. But since you have a CNF can't really shrink, can it? Or
yeah. I mean, shrinking is the opposite to swelling. So swelling is the interaction with water. So you basically always have some water in between fibrils, fibers, cellulose backbones. And I think you just move them chemically more together by this hemiacetals. I'm not sure if you do an oxidation, does it then breathe again? Does it swell again? If you get rid of the cross-linking probability there?
I don't think we have directly tested that.
Haven't. No.
I somehow doubt it, because the shrinkage is so massive. I mean, it's not orders of magnitude, but a factor of many.
But cellulose, in a way, is surrounded by water. In this, the OH groups, they keep a certain distance, and if you take that away by making a little bit more stronger hemiacetals, then just like a hydrogen bond, maybe that can explain at least part of it. But I cannot offer you anything smarter than that out of my head.
Please let us know if you
we can think about it. Yes.
Yeah. Thank you so much.
Is it okay, Lars? Do you have a question?
No, it was more to fill up on that. The only thing we looked at was if you compare ethanol or the aldehyde or an alcohol, they have very different vapor pressures. So they seem to behave differently. But then it's, of course, the surfaces are dominating the properties of the cellulose in this case. So, but we are still bewildered. Yeah.
Mm.
So I can continue with one question. I think it was on slide 21 where you talked about, I think it was the alcohol cellulose, and I was coming to the yield. Yeah, here you mentioned the yield. Can you elaborate a little bit what you mean here with yield? Is that, yeah, what do you mean with this yield? And
yield is what we can recover after the oxidation and reduction.
So that is what you, relative to what you injected, or?
No. this is the yield of the macroscopic oxidation reduction.
Okay. Mhm.
This is not the recovery on the sec.
So can you say something about what is the recovery in the sec? Is it 100% or close to?
It's never 100%.
No.
But if you have a good state of dissolution, I mean, the recovery of the sec always depends basically how well you measure what you inject, right? So, the only thing what I can say here is we usually have some average numbers because we measure basically celluloses 24/7. So we usually dissolve a certain amount, or let's say we start the dissolution process with a certain amount, and we know roughly what comes out in terms of recovery. For the dealdehyde celluloses, it goes down, of course, with a degree of oxidation. But if the recovery in the process is really bad, then we don't use the data.
Okay.
Because then it also means you don't dissolve a lot. You know, so there is a limit to it. So if then recovery drops under a certain point, it doesn't make sense, because the question is, where's the rest of the sample? And if the rest of the sample is 80% and you only recover 20%, it's meaningless, you know.
Yeah, I fully agree. Lars, do you have something more?
No. Yeah, maybe one question, and that was I was astonished by the sensitivity to pH here. If I look, if it's one of the connecting curves here, if I noted it correctly, you start to go down to up to 8.4, you see a significant change immediately. Yeah. So it's really sensitive. I thought it was a bit above 10 or something, but it starts much earlier.
Yeah, it starts above 7 basically.
Yes.
And this is great concern for a long time, or also in paper conservation. If you have an historic paper with keto groups and you run those papers in a mass deacidification, which is basically pH 8, 9 something, the fear is always like that you degrade more by beta elimination than you do good for that papers. And we look a lot into that, and we also have processes which we call diagnostic beta elimination. So we do beta elimination in order to figure out where at the cellulose backbone oxidation has occurred. You can basically use that when you say, okay, if my oxidation is hypothetically in the middle of a chain, and you bring that into an alkaline environment, you split this chain into 2 halves. So you have a large drop in molar mass. If your oxidation occurs at the ends of your chain, reducing end or even non-reducing end, you bring it under alkaline conditions, you do beta elimination, but you split off like 1, 2 anhydroglucose unit, maybe 5, 10, still your molar mass is more or less stable within the limits we can measure. So you can basically say, okay, if you have an oxidized material and you take it into an alkaline solution and you watch the molar mass degradation, you see a little bit also where that happened. And when we look here at this periodate, we can basically say if we have such a large drop, that oxidation also occurred really along the chain, not just at the ends, which is the amorphous ends, which are maybe better accessible. So it tells us basically where it happened.
It was a super interesting presentation. I really liked it. But Lars, is it time to? I don't see any questions in the chat.
No, Per has the hand raised, but is it a new or an old hand, Per?
That's an old one, sorry.
Okay, so it's not old, no worries. Well, I'm happy so far. That's
and we don't seem to have any questions from YouTube either. So
thank you so much, Antje, for sharing your knowledge, deep knowledge in this area. We'll probably come back with some questions too.
Yeah, I wanted to say
later on.
if something comes up later, just let me know. And
Yes.
yeah,
Thank you a lot. Thank you a
Yes.
lot.
thank you. Thank you.
Yes.
Okay.
Thank you. And thank you
Okay.
for all,
Then-
everyone who's been listening.
Yes.
Yeah.
Thank you.
Bye-bye.
Bye
Bye
bye.
bye, and good luck with the lecture now.
Yes.
Yes. That was in German now.
Okay. Yeah.
Bye-bye.
Bye bye.